move to the next speaker, which is also the last speaker of the workshop today, Professor Simon Solvable. So when I'm introducing you, you might start sharing the screen. The next speaker would be Simon Solvable. He's an assistant professor in the Paul Allen School of Computer Science and Engineering at the University of Washington. His research interests are broadly in machine learning, such as deep learning, representation learning, and reinforcement learning. Prior to studying as faculty, he was a postdoc at the Institute for Advanced Study of Princeton, hosted by Sanjeev Arora. He completed his PhD in machine learning at the CMU, where he was co-advised by Ati Singh and Barnabas Pocos. Previously, he studied EECS and EMS at UC Berkeley. He has also spent time at Siemens Institute and the research labs of Facebook, Google, and Microsoft. Today, Simon will talk about offline multi-agent reinforcement learning. The floor is yours, Professor.
All right, thank you very much for the invitation, and it's a great workshop. So can you see my screen, just to double check?
Yes, we can see that.
Okay, yeah, so today I'm going to talk about our recent work on offline multi-agent reinforcement learning. So in the first part of the talk, I will kind of review what we know for offline reinforcement learning. And offline reinforcement learning is a very important topic in many applications, and we will also ensure some safety guarantees if you want to deploy a policy just from the offline data. So here I will mainly talk about from a theoretical point of view, like when you can actually find a good policy in a single agent and multi-agent settings, such that the policy deployed is actually safe and optimal. All right, so why we study offline reinforcement learning? So there are mainly two settings in reinforcement learning. One is online, where you can control an agent which is interacting with an environment, and then you get some data from the environment to train your policy, and then you interact again. And in many practical scenarios, you don't have the resource, or it's very costly to actually interact with the environment. Instead, you only have a lot of offline data from prior experience, which may be the data may be collected not from the open policy, but some some random policy or some behavior policy. Okay, so in many applications like medical domain, recommendation systems, transportation, etc., you only have offline data. It's very costly to interact with the environment. So here, this talk is about suppose you have a large amount of offline data, but when you can actually find a good policy from offline data. It's not that every policy you find every data set you have will give you a good policy. You need some good data such that you can find a good policy. So to motivate offline reinforcement learning, you can look at this medical domain application where you model the procedure of taking like a treatment, and in which each step you have multiple steps, and each step you can model that as a state, and whether to take a medicine or not is kind of an action. So for this kind of application, it's very costly to actually do online exploration because the agent is here, it's the patient, where you can't really do multiple experiments on the patient, but instead you have a lot of offline data, and you can only use this offline data to design the best treatment plan. All right, so the first part of the talk, I'll talk about what we know about single agent reinforcement learning in the offline setting. So now let me specify the setting a bit. So here you are controlling an agent which is interacting with an environment. So at each time, you are at some state, say ST, and the agent will take some action, AT, and the environment will transit the agent to the next state according to some transition matrix or transition function that depends on the current state and action. So now you map to the next state. This transition can be stochastic, and also the agent receives some reward. Okay, so here we focus on a kind of simple setting where it's called episodic setting, where you just repeat these interactions for h times, And H is also called the planning horizon or the episode length. The result here can be generalized to, say, discounted setting as well. All right, so policy, which you want to learn, it's you can mathematically it's a mapping from the state to action, okay? And the goal is to maximize the value function. Basically, the goal of the agent to maximize the expected total reward, where the expectation is over the transition, and the reward, which can be stochastic. Also, your policy can be stochastic as well. Okay, so the goal is to maximize the expected total reward. So in general, because everything is stochastic, so you may not find the exact optimum policy. You may find, say, often we call near optimum policy that is very close to the optimum one. So let's say V star, it's a value function of the optimum policy. Your goal is to find some policy at pi, such as very close to the optimum policy, say within epsilon accuracy. All right, so one of the canonical setting in reinforcement learning is called tabular Markov decision process. So it is kind of a stylized setting because we only have a finite number of states, finite number of actions, and say reward, say some scaling, let's say it's from 0 to 1. And the number of samples data you have to learn, say, a neural policy will depend on these parameters, say SA, H, and 1 or epsilon. So this is definitely a simplified setting. In practice, so number of states, number of actions is very large. But only looking at this kind of stylized setting, we can still get a lot of insights of when we can actually learn a good policy from the offline data. And this is what my talk is mainly about. Although there are a lot of work actually generalize this result from tabular setting to a more practical setting, including using function approximation, neural networks. I'll briefly talk about those results in one slide later. All right, so for offline single agent reinforcement learning, what we do is we collect, say, n data points. But here, each data point is actually a trajectory, okay? So let's say we have some policy to do data collection. So here we use the rho to denote the data collection, or in the literature, we often call it behavior policy. So so given this rho, and of course you have a transition matrix and reward reward distribution, then they will together induce a distribution or the state, the action, and reward. And this will generate your data set in the offline reinforcement learning. So this is your data set form. You have n data trajectories, and each trajectory is H steps. Each step you have a tuple, which is the current state, current action, and reward you receive from the current step. Okay, so this distribution, we often use the rho and to denote distribution of that generates this offline data set. Okay, so this distribution will depend on the data collection policy and also the transition matrix P. So our goal again is to learn a policy pi from this data set D, such that this is very close to the optimum policy, so within epsilon error. Okay. All right. So one of the most fundamental questions in offline reinforcement learning is that what kind of condition do we need such that under which we can actually learn a new optimum policy? Okay. So you can imagine. So suppose this behavior policy is kind of unrelated to the optimum policy at all. Okay. So suppose optimum policy at a certain state take action A, but this behavior policy always take action B, then basically can have no information about what is an optimal policy, right? So you need some condition about your behavior policy, or your data collection policy, such that you can actually learn a new optimal policy from data set that collected from this behavior policy. And this is what our theory studies. So for single agent reinforcement learning, what we need through years of research, we find that what we need is the following condition. It's called single policy coverage assumption. Okay, so this assumption states that the behavior policy only needs to cover a single open policy. Okay, so this is necessary and sufficient. For a necessity, you can see that if your behavior policy does not cover any open policy, then you cannot hope for to recover an open policy. And later I'll show you also this is a sufficient condition in the sense that with a polynomial number of samples, and if you have this condition, you can actually recover a null policy. So this is a more formal statement about this assumption. So this assumption states that there exists some constant, as I say, single, such that the density ratio between the distribution induced by the open policy, which is pi star, and the distribution induced by this data collection policy. So this density ratio is upper bounded by some constant. And the number of samples you need to find in your policy will depend on this constant as well. Okay, and requires for every state action pair. So here, if you're basically what it says is that if you're open policy pi star, choose this action A as this state S, and then in your data collection policy, you also need to at least have some probability of choosing A at this particular state S. Otherwise, this single will be infinitely large. But of course, on the other hand, if this at some state S is pi star does not choose action A, then the numerator will be 0. So whatever denominator is, you can have C single will be 0. But here, C single is like uniform upper bound for all state action pairs. So at least you need to be finite for the open action chosen by this open policy. So the single, in the best case, if this row your behavior policy is exactly the same as pi star, then it will be 1, which is kind of the best case. On the other hand, if it's if the row does not cover the pi star for some action, then this can be infinite. So it kind of covers our intuition that your behavior policy need to cover the open policy. So to show, with this under the assumption why we can actually recover open policy, the main algorithmic idea is called pessimism. So this is a kind of line of recent work showing both in theory and empirically, including some deep neural network experiments showing this pessimism is very useful. So I will show you what this pessimism is in the next slide. So basically, empirically using this pessimism, you can actually achieve good result. In theory, there's a line of work about you can get minimax sample complexity, and our recent work can get more fine-grained result for a particular problem instance, which is called the gap-dependent bounds. So I will give you one slide of what is pessimism. So basically, so here's a very simple example. So suppose you only have one state and you have, say, 4 actions, A, B, C, D. And so here QA represent the value of action A, or if basically the Q function of the action A. Okay, and similarly for QB, QC, and QD. Okay, so what you have is to compute a confidence interval for each of the action. Okay, so for tabular setting, just by counting, and there's some well-studied confidence interval construction for each of the action. Basically, you can take the scale with 1 or square root of the number of data you have for each action. Okay, so here you have this orange line, which is the your empirical mean of the each action. Okay, that's the orange line, and you also have this box, which is the confidence interval for each action. Okay, so you have both upper bound and lower bound. So the main algorithmic idea for pessimism is called is to, for example, for this example, is to choose the action with the highest lower bound. So you can see here, you will not choose the action that has the largest empirical value, which is action A. You can see here, action A's orange line is the highest, but you will not choose that. You will choose the action with the highest lower bound. So you can look at the lower bound for these 4 actions. What you choose is to choose the action B, which has the lowest, which has highest lower bound. Okay, so with this algorithm, or algorithm idea, you can design specific algorithm for different settings. For deep neural networks, you can also deep Q network can also design some similar algorithm, but the principle is the same. It's based on this pessimism. You build some confidence interval, and you choose the action that has the highest lower bound. So this is about the tabular setting. So here's one slide about what we know of going beyond this finite state action setting. Is we often call it large state space setting, where you need to use function approximation either about the model or the value function, the Q function, to generalize of core states, because the state space are large. You don't want touch every state, which is sample-wise inefficient. So there's some line of results showing if you only assume the optimal Q function, Q star is linear, or if it can be represented by some neural network, this is not sufficient. You need some additional assumptions such that you can actually learn your whole policy. So there's a very impactful result showing this is a separation between the supervised learning and reinforcement learning. For reinforcement learning, you need something more. So there's some line of work showing what you need for some additional assumption that can permit polynomial sample complexity for the alpha setting, including some transition model. If you use a function approximation for the model instead of for a Q function, you can actually recover policy. And there's some other things called assumptions called domain completeness, and some realizability about density ratio. If you're interested, we can talk more say after the talk. So this is about single agent reinforcement learning. But nowadays, we often need to deal with environments that have multiple agents. Okay, so generally speaking, multi-agent reinforcement learning is about study how multiple agents interact with each other in a common but unknown environment. So some classical example include Go and different games, and more recently there are many environments like cooperative robotics and AI economists from Salesforce, where they study how different agents interact with each other and how they give some economical behaviors. Okay, and each agent's goal is to optimize its own long-term return by interacting with environments and the other agents. So here today, I'll instead of talking about the fully general sum multi-agent reinforcement learning, I'll talk about one specific case and give you a sense of how this multi-agent is significantly different from the single agent reinforcement learning. So what is this simple example? This is called two-player zero-sum Markov games. So it's a very it's a classical model, and there are only two players, and these two players compete against each other. Okay, so it's like playing one versus one game, like Go, like poker, and computer games, investment. So although it's simple, it has a lot of applications. So for multi-agent reinforcement learning, the goal here is to find a Nash equilibrium. So what is a Nash equilibrium? It's a pair of strategies, one strategy for each player. And the goal is such that this pair of strategies that no player can do better by unilaterally changing the policy. Okay, so at this policy pair, no matter no player can do better by changing its own policy. Okay, so basically that's like an equilibrium. Okay, so that's a standard notion of Nash equilibrium. And our goal is to find the Nash equilibrium in this two-player zero-sum game. So mathematically, the setting is very similar to single agent setting, except that now we have two agents. So now at each time step, again, these two players are at some state, and both of them will choose action. And then the environment will transit the state to the next state. So the transition will depend on the state and the actions chosen by both players. Also, this environment will reveal some reward that depends on state and the pair of actions. So remember, this is a competitive game. So we have two players. One is trying to maximize reward. We call it max player. The other is called min player. And the goal of the max player is to maximize total expected reward. Min player's goal is to minimize expected reward. So that's why they are competing against each other. So for the example I will show in the following, I will mainly talk about even simplified version. It's called zero-sum bandit. So there's no transition at all. There's only one state. And so here only the reward matters. So basically for this special case, zero-sum bandit, you have H equals 1 as fixed state, and only the word matters. And basically, you have two players. Each episode, you only choose one action, and one tries to maximize reward, one tries to minimize reward. So although we only studied the simplified setting, it already illustrates a lot of insight about why multi-agent reinforcement is significantly different from the single agent reinforcement. And again, we'll consider this simplified tabular case. You have finite number of states, finite number of actions for both players. And generally, the sample complexity will depend on these parameters. So now for each one player has number of actions A, the mean player have number of actions B. So similar to the single agent setting, we have some behavioral policy, but here is a policy pair to collect the data. Again, we use row to denote this policy pair. And so this row will again generate a data set of n trajectories. Each trajectory has length h. And for each time step, you have a state, a pair of action, and a reward. So again, this distribution of the state and action pair is determined by this data collection policy row and the transition P. Okay. So again, our goal is to learn a policy pair. We denote as mu and nu, that is epsilon close near, or it's very close to a Nash equilibrium. Okay. So again, the most fundamental question we study is like what condition we need to find an epsilon close Nash equilibrium in this the simplest multi-agent reinforcement setting. Okay. So the first thing you may consider is to generalize our condition in the single agent setting to this multi-agent setting. So remember, in a single agent setting, what you need is that your behavior policy to cover the optimal policy, okay, one optimal policy, and that is enough to recover the optimal policy. So here, suppose our behavior policy, policy pair row, covers Nash equilibrium policy pair, which is known as mu star nu star. So this is a formal definition. The density ratio between these two is upper bounded by some constant. So is this simple assumption enough for the multi-agent reinforcement learning? Okay. So our first result is to show that there's a significant difference between multi-agent and single agent reinforcement learning in the offline setting. That for the multi-agent reinforcement learning, actually this assumption alone is not sufficient. So here's our simple example. So it's a very simple example, but already illustrates significant separation between the single agent and multi-agent reinforcement learning. So here you only have you have two games, game 1 and game 2, and you have two players, say max player and two players. Each player only has two actions, A1, A2, and B1, B2. So for game 1, okay, so if you take A1, B1, you get reward 0.5. If you hit A1, B2, you get reward 1. A2, B1, you get reward 0. A2, B2, you get reward 0.5. So for the max player, remember, its goal is to maximize reward. So if for a max player, it's always better to choose action A1, because for either the mean player choose B1 or B2, you choose A1, you get better higher reward. And for the mean player, it's always better to choose reward B1, because for either the max player choose A1 or B1, you choose B1, you can have lower reward. So this together will make A1, B1 a Nash equilibrium for this game 1. Okay. And for game 2, the only difference is that we switch reward for A1, B2 and A2, B1. Okay, now A2, B1, you get reward 0, A2, B1, you get reward 1. So here, for the max player, it's always better to choose action A2. So you can see here, for either the mean player choose B1 or B2, it's always better for max player to choose action A2. And similarly, for a mean player, it's always better to choose B2. Okay, so you can see here, the only difference is A1, B2 and A2, B1. So now consider you have data set which only have information, covers the information about A1, B1 and A2, B2, say each with 1/2 probability. So now you will have this parameter C single equals to 2 because it's 0.5. Also, this offline data covers both A1, B1, and A2, B2. So it does cover the Nash equilibrium. However, if you are looking at the data set you have, you only know A1, B1, you have reward 0.5, A2, B2 also have reward 0.5. So you cannot differentiate whether you are in the game 1 and game 2. And if you output a Nash equilibrium, either A1, B1 or A2, B2, you do not know whether they are Nash equilibrium in your specific game because you don't know whether you're in game 1, game 2. So this simple example shows this single policy coverage is not sufficient for multi-agent reinforcement learning. So here, at least for this example, we need to cover A1, B2, and A2, B1. So here's our proposed assumption. So I'll not go into the mathematical detail, but basically what you need, suppose A1, B1 is Nash equilibrium. In your mind, what you need to remember is that we need to cover the entire column and the entire row. So basically, suppose this is Nash equilibrium, your data set need to cover not only this particular Nash equilibrium, you also need to cover all the associated, so A1 and B2 to B, so all this entire row and the entire column as well. With this assumption, you can actually recover a Nash equilibrium, which is A1, B1. So this will be qualitatively larger than the single policy coverage, because even for the minimum, you need this constant will be, say, A plus B. So there are some other entries in this matrix game, but you don't need to cover them. It doesn't matter. As long as you cover the entire row and column, you can recover a Nash equilibrium. So here's a high-level idea of the algorithm to recover a Nash equilibrium. So again, you will compute a confidence interval for each of the action pairs. And you compute Nash equilibrium for each Nash based on the lower bound and the upper bound. And then you will return the policy for the max pair computed from the lower bound, and return the policy for the mean pair computed from the upper bound. Okay, so that's corresponds to mu under bar and mu upper bar. So again, this shows a form of pessimism because you compute the max pairs policy from the lower bound and mean pairs policy from the upper bound. So again, it's a pessimism. And for those who are interested in sample complexity, this is what you can get. You can find absolute close Nash equilibrium with this number of samples you have. So again, it depends on this constant characterized coverage. So also have some examples showing, this unilateral coverage assumption cannot be weakened. If you have one entry that you do not cover, you cannot still differentiate two games which are kind of conflicting Nash equilibrium. All right, so to conclude my talk, I will talk about so there are basically two takeaways from the offline reinforcement. One is about coverage assumption. Like suppose you want to output a new policy and deploy it safely for the real world environment, you need to consider what data you actually have. Okay, and also related to the problem structure you have. So suppose you only consider single agent reinforcement, you only this kind of a weak single policy coverage assumption. And if you have two-player zero-sum games, a more general finding Nash equilibrium in general sum games, you need this kind of unilateral coverage. So more recently, we study the congestion game, which has a lot of applications in transportation, where you actually need weaker condition than the unilateral coverage, but stronger condition than the single policy coverage, which we call one-step deviation coverage. So for offline reinforcement, you need to consider what problem structure you have and what kind of data you have that covers the state space such that I can actually recover your policy. And the main takeaway from the algorithm is called pessimism. You only use pessimism to penalize uncertainty state actions such that I can actually recover your policy. And together with pessimism, you can use existing reinforcement algorithm like value iteration, policy iteration, or say PPO, policy optimization algorithm as well. And lastly, I want to acknowledge my student, Qimeng Cui, who has done most of the work for the offline multi-agent reinforcement. And I can take some questions. And thanks for listening.
Thank you, Professor Du, for the wonderful talk. So let's see whether there are questions. And actually, I have a question about this zero-sum game. It is actually a very interesting work on recovering of policy of like Nash equilibrium policies. So I was wondering, so in this case, do we assume that there's the Nash equilibrium policy exists in the data set, or it's unique?
Oh, that's a good question. So first, you need to assume, definitely you need to assume it exists in your data set. Otherwise, you basically cannot hope to recover this Nash equilibrium. Like if your data set does not contain any Nash equilibrium, and you have no information about the other Nash, Nash equilibrium in not in the data set, you cannot hope to recover the Nash equilibrium. However, it doesn't need to be unique. Suppose you have two Nash equilibrium, as long as you have data set cover one of them, and with this kind of unilateral coverage assumption, you can recover that particular Nash equilibrium. So yeah, so for an offline reinforcement learning, generally don't need the uniqueness for Nash equilibrium or open policy.
Okay, so if the Nash equilibrium is not unique, so can we guarantee which policy pair can we recover or not?
Yeah, that's again a great question. So generally, you cannot guarantee which particular Nash equilibrium you recover. However, in certain cases, suppose what we call there's a gap between the Nash. So okay, suppose in the case that your Nash equilibrium is deterministic. So in the general case, your Nash equilibrium is a stochastic policy over the actions. So you may have some deviation from the exact Nash equilibrium, and it's hard to guarantee that you can recover that exact one. But if this is deterministic and the value has some gap with the other entries, then you can actually recover it with using offline data.
Thank you. Let's see what there are other questions. Well, actually, so if there are no other questions, I think I'll hand over to Shangding for concluding the workshop.